An electrocardiogram, or ECG, or the Dutch or German version of the word EKG, is a tool used to visualize the electricity that flows through the heart. An ECG tracing specifically shows how the depolarization wave moves during each heartbeat, which is a wave of positive charge. And the way it looks depends on the set of electrodes you're using. This particular set of electrodes is called lead 2, for example, with one electrode on the right arm and the other on the left leg. So essentially, when the wave's moving toward the left leg electrode, you get a positive deflection, like this big positive deflection corresponding to the wave moving down into the left and right ventricles. To read an ECG, it's really helpful to first understand what a normal sinus rhythm looks like. To do that, let's look at a single heartbeat on an ECG from the viewpoint of lead 2. In a healthy heart, everything starts at the sinoatrial node, or SA node, which is a little patch of tissue in the wall of the right atrium full of pacemaker cells. When one of these pacemaker cells depolarizes, a wave of positive charge spreads outward, and overall it moves from the SA node towards the apex of the heart. So it aligns pretty nicely with the lead 2 vector. Now, the heart muscle cells are often described as having a functional syncytium, because even though each one cell has its own membrane, the cells also have tiny connections or openings between them. That means that during a depolarization wave, ions can flow right from one cell to the next. Now, it's also important to mention that the depolarization wave moves at two different speeds through the heart. In the pacemaker cells, which are special types of heart cells laid out like highways through the heart, it moves super fast, but it moves more slowly through the rest of the myocytes, which do the contracting. If the pacemaker cells are acting more like highways, then these types of cells are like cars moving through congested small streets. Now, the ECG measures out changes in time on the x-axis, where one small box is 0.04 seconds, and voltage on the y-axis, with each small box being 0.1 millivolts, sometimes called 1 millimeter. And 0 is called the isoelectric line. And then so the tracing shows positive or negative deflections away from this line. So a depolarization wave starts in the SA node, then goes through the atrial internodal tracts, also called Bachmann's bundle, over to the left atrium so that both atria basically depolarize together. The overall direction of that depolarization wave is in the same direction as the lead 2 vector. So there's a positive deflection on ECG called the P wave. Meanwhile, the signal also gets carried from the SA node to the AV node, where it gets delayed just a bit. And this allows the atria to fully contract and fill the ventricles with blood. During this delay, there's no depolarization wave moving towards or away from lead 2. So this shows up as a flat line, and the interval from the beginning of the P wave through this flat portion is called the PR interval. From there, the signal goes through the pacemaker cells that make up the bundle of His, and then into the left bundle branch and the right bundle branch. In addition to moving through the fast pacemaker cells, the signal also goes through the slow myocytes in the interventricular septum, in a direction that's slightly away from the lead 2 vector, since there's a ton of tissue here, and this creates a tiny negative deflection on the ECG, which is called the Q wave. From there, the depolarization wave flows down into the Purkinje fibers. Since the largest vectors are the ones in the left ventricle, which is roughly in the direction of lead 2, this creates a large positive deflection on the ECG, which is called the R wave. The apex of the heart depolarizes first, but then the wave moves back up to depolarize the top of the ventricles, which is in a direction away from lead 2, causing a slight negative deflection on the ECG, which is called the S wave. Together, ventricular depolarization creates what's known as the QRS complex. After tissue depolarizes, there's a brief period of time where there's no change in electrical activity. So the ECG goes back to the isoelectric line. The exact point at which it hits that line is called the J point. And for a brief time, there's no net change in electrical activity. And this is the ST segment. After that, the ventricles have to repolarize, or become negative again, to reset itself in preparation for another wave of depolarization. Now, repolarization moves in an overall direction upward, opposite the direction of lead 2. So you might think that it should be a negative deflection, right? But really it's still a positive deflection, since this time it's a wave of negative charge. So essentially now when it's moving opposite to lead 2, it's a positive deflection on ECG. And this final wave is called the T wave. The T wave is more spread out over time than the QRS complex because repolarization is a slower process that takes place at slightly different times for each cardiomyocyte instead of happening all at once like depolarization. It's also worth mentioning that atrial repolarization doesn't usually show up at all on an ECG because the small vectors created by it get lost in much larger vectors that get created by the QRS complex. Alright, as a quick recap, on an ECG there's a P wave, which corresponds to the atrial depolarization wave, then an isoelectric line where the depolarization wave goes through the AV node. After that there's a QRS complex, which represents ventricular depolarization, followed by another brief isoelectric pause, which is the ST segment. Finally, there's a T wave, which represents ventricular repolarization,